Okay, so doing a quick sound check. If you can hear me, go ahead and raise your hand on the control panel. For our panelists, go ahead and turn off your microphone so you don't get any feedback when each other are talking. Let's see, can you hear me there? The people in the audience, can you hear me? There we go. We got one hand up. A couple of people have woken up. That's a good thing. And I can see the person that clicked it. It's about 8 o'clock in the morning their time, because it's 11 o'clock where we are. Good stuff. Loading up very quickly. Nice to see everyone hopping on the webinar with us. Just like every time we do this, once a month, it's always great to see everyone hopping on our webinar. Okay, the clock just clicked over and here we go. So good morning from Virginia. Is where I sit, and really glad to have the opportunity to spend some time with you on this webinar. Today's program, Building Codes and Fire Test Standards Around the World, has quite the esteemed panel. Abhishek Chabra joins us from Dubai. Dr. Gabby Peck joins us from New Zealand. Rich Welke joins us from the Chicago area, about 45 miles northwest of the city, and I'm sitting about 70 miles east of Richmond, Virginia, about 2.5-hour drive south of Washington, D.C. So, yep, we're around the world, not only just in name, but take a look where we sit. We are virtually around the world. You know, the FCIA, real quick, if I wasn't doing my job, I wouldn't do my quick plug about the FCIA and the things we've done. You're going to hear the DIIM worldwide today. But know that the FCIA collaborated with organizations to build this DIIM. We called UL, we called FM approvals, and then worked with them to develop those two programs to set contractors apart. We, at a conference in San Antonio, Texas, one of our members said, how come there's no special inspection to term in the International Building Code, special inspection, in other words, mandated inspection of fire stopping for certain types of buildings. Why doesn't it exist? The ICC said you don't have a standard and you haven't come to put it in the code. So that's why the FCIA Standards Committee exists, is that they built that standard at ASTM with our manufacturer partners and implemented into the building code. Why isn't there accreditation for inspection agencies, just like we've got the FM and UL programs for contractors? Well, that's where the IAS AC 291 came from. And why isn't it in specification? Well, it is now because the FCIA built it and put it in specs. Our FCIA has been all over the place the last 25, actually 27 years. 1998 June is when we started this association, 8 of us. I was one of the founding members, got out of the contracting business and became the executive director, now technical director. Thankfully, Lindsay Dupkowitz has stepped forward and is doing a fabulous job of taking the association forward, and will for the next several years, because she's a lot younger than both Rich and I. Anyway, we're everywhere. Look at the guy on the screen. That's Rich testifying in the International Code Council hearings. Bill Koffel, our code consultant, lower left in the picture also. Our team together have been working together on and off since 1994, before the association existed. We advocate on behalf of the FCIA and the DIIM, which you'll hear more about. I want to spend just a couple of seconds about the publications the FCIA has put together. That manual of practice was assembled in 98, 99, and 2000, published in September of 2000 for the first FM fire stop exam in November of 2000. It has had another 7 editions since then, with updates every 3 to 5 years. Look for one coming in probably 2026 as well. From the MOP comes the Fire Stop Education Program, Level 1, Level 2, Level 3, and soon Level 4. A great price point for education of your whole company, unlimited use, pretty amazing stuff. That program is as deep in fire stopping, is deeper in fire stopping than anything else you'll ever see. It's a great program in addition to the manufacturer education that you would get, because each manufacturer has different chemistry. Their products make sure to hang out with them too. The Life Safety Digest, Lisette and I are working like crazy on it, the next issue, which will publish sometime in June. We've got some great articles coming on healthcare type occupancies. If you advertise in Life Safety Digest, thank you. It's a labor of love because we don't make tons of money on that. It's about getting the word out on fire resistance rated assemblies. In the circulation, it's worldwide, it's electronic, it's print, it's both. Really cool stuff. The most fun I have, though, is traveling the world, getting to see our friends, whether they're in Canada, Dubai, Mumbai, Abu Dhabi, Doha, doesn't matter where they are. We love hanging out with our friends throughout North America, South America, Mexico, and other places. I'm not going to spend time on this, but know that the FCIA built these standards to increase the reliability of installed fire stopping around the world. So at this point, I'm going to click to the next slide and ask our friend Abhishek Chabra, FCIA's Director of International Initiatives, and a guy that's really done a lot in this industry and continues to make a difference wherever he goes. So Abhi, the floor is yours. I'll let you have at it.
Thanks, Bill, and a big welcome and a big hello to everybody who's joined in. And I'm guessing from almost all parts of the world, as we, as a large industry collective, continues to grow. As some of you know, my task is to make more friends, as Bill mentioned, and expand our good work across various parts of the world. If you could see, there is a nice kind of a ticker running on the left of the screen in the form of this video, which is showing how we have been growing almost everywhere in the world now. And I'm very excited to share that the basis of our design, install, inspect, maintain construct as a framework is something that allows the industry worldwide to assure not just better fire stopping, but the framework as supports all of passive fire protection in intent. So I'm going to very quickly talk about how we are here and then pass the baton to my esteemed colleagues and friends. Bill, if you do the next slide, please. So Bill talked about it, and all the friends of FCIA are very familiar in most likelihood about our quality management based framework of design, install, inspect, and maintain. Bill, next. This construct has helped all users of the construction industry speak the same language. And this begins with design. And as our education has been going on and will be expanding, that we talk about and educate all stakeholders about the fundamental common design approach, which may be spoken in different languages in different parts of the world through different building codes, through different technical specifications, but the intent remains the same, which is how clearly passive fire protection needs to be designed. With the emphasis on design being harmonized almost all over the world, we move to assuring installation and inspection through standard regimes and concepts that make sure that the installation and inspection are delivered accurately. Some of you know we have worked extensively on not just continuing to upgrade the manual of practice, but we have been growing our standard and code agnostic education in order to ensure that each stakeholder involved in installation, wherever they may be, they understand the whole process, which heavily relies on assurance. While the whole framework has been increasing the reliability and assurance of fire stopping, heavily dependent on how we have implemented the credentialing systems. Today's session draws its attention to a very strong framework of assuring fire stopping. I often get told that fire is exactly the same, whether you are in Chicago, in Florida, in Richmond, in Wellington, in Dubai, in Mumbai, wherever you go in the world, the fire is exactly the same. Then how come there are so many different standards to evaluate the behavior against a fire exposure? And this is a very interesting and an exciting topic of debate sometimes, but today we intend to bring this large piece of knowledge and bring about the fact that how the intent of the fire tests, which could have evolved and originated from different parts of the world, remains exactly the same. So with that, I welcome my friends. Over to you, Bill.
Thanks, Avi. I'm going to send the screen over to Rich Walke, who's going to start us through North American-based codes and standards. So, Rich, the floor is yours, and if you need, hop in, let me know, and I'll jump in.
Okay, great. Yeah, feel free to jump in at any point. So good morning, good afternoon, good evening, or middle of the night in Gabby's case. Thanks for joining us here today. We really do have a unique program to present to you today. And in the past, Bill and I have presented on worldwide standards for fire resistance, worldwide standards for fire stopping, but we're not experts on the standards and testing and code requirements worldwide. We're US focused, Canadian focused, and we're learning the testing in other parts of the world, but we're not truly the experts. So today we do have the experts on the panel with us. So thanks for joining us here for this unique experience. So let's talk about first the North American standards. So that's my role here today, is to kind of give you a little bit of history on both fire resistance standards and fire stopping standards here in the US and in Canada. So in the 19th century rather, the differentiation between fire resistance and non-combustibility was often confused. The early codes required non-combustible construction or protection by non-combustible materials, thinking that meant that the building would withstand a fully evolved fire. That didn't necessarily prove to be the case. Non-combustibility may not equal fire resistance due to the spalling and fracturing and delamination of some of the non-combustible protective materials and the methods of attaching those materials. And as fire incident reports became available, these intuitive methods really proved to be inadequate. And that led to some furnace testing. The first furnace fire tests in the US were conducted in 1890. And that kind of turned the focus from intuitive methods to more tested and proven systems, but perhaps even that was not adequate. The 1906 San Francisco earthquake generated many lessons on how not to fireproofing, showing that some of the intuitive methods used earlier really were not adequate. Some of the protection materials delaminated, tiles cracked when hit with water from the firefighting efforts, or the steel, which may not have been protected, softened, lost its strength, and ultimately allowed for collapse of some of the buildings. So we learned a lot from that fire, unfortunately, and that's the sad thing about this industry, is we learn by tragedy. But we did learn from it. Shortly thereafter, we here in the US started developing dedicated test furnaces for establishing fire resistance ratings. UL had or built 3 furnaces in the early 1900s. Their wall furnace was constructed in 1903. Reality, though, the focus was not fire resistance of the wall, it was fire doors. How do we protect that breach or opening in a wall assembly that we presumably thought was fire resistance already? So that was the original focus of that wall furnace. And then the floor furnace came on stream in 1912, column furnace in 1917. So at this point, we now had the ability to evaluate materials, systems, assemblies by standardized methods. ASTM published the first standard for fire resistance in 1918. It was identified as ASTM C19, and it covered floor assemblies and non-load bearing partitions. And interestingly, that standard used the standard time temperature curve that was developed by UL in 1916, and that curve remains unchanged today. So when we talk about the standard time temperature curve later on in the program, this was a curve that here in North America dates back to 1916. And ultimately, a few years thereafter, UL published their standard for fire resistance, UL 263 in 1929. And 1947, ASTM renumbered their standard C19 to ASTM E119. Presumably, they kind of fit the then current or new numbering sequence for their standards. There were a number of evolutionary changes which took place in the fire resistance standards back over the years. One of them was the removal of the hose stream criteria for floors and roofs in 1953. Now, why was that done? And people forget history, and sometimes, I guess, I'm not a student of history, but I like to think back, why did we do certain things when writing these standards? There was a reason for that in 1953. The reason for is UL had conducted 30 to 40 years worth of hose stream tests on floor assemblies, roof assemblies. Never once had there been a failure. So that test was a very a very evasive test, did tremendous damage to the furnace every time it was conducted, because you had that cool water dripping down off of the assembly into the furnace, into the hot furnace. So ultimately, UL, and it's not just UL, I shouldn't say it, it's the standards rating committees made the decision in 1953 that we've never had a failure. This is truly beating up our furnaces. Why do we need to run the test? So it was removed from the standard. But what we didn't do a good job of is remembering why it was removed when we wrote other standards, such as the standard for fire resistant joint systems. The hose stream is not a requirement for fire resistant joint systems and horizontal assemblies. Why? Because the folks back when the joint standards were being written said, oh, it's not required for floors by E119, so it shouldn't be required for joints. Well, that's a flawed logic. There was a reason it was removed from the fire resistance standard. There was no reason for it not to be incorporated into the joint standard. But anyway, I've digressed here. So let's just move on. So the concept of restrained versus unrestrained ratings, which is certainly very controversial right now, was introduced in the standard in 1973 after probably about a 15-year discussion within the ASTM Standards Writing Committee. There was a load restriction condition that was introduced for testing assemblies which were loaded to less than 100% of their capacity, and that occurred in 1976. And then a few years thereafter, ULC, Underwriters Laboratories of Canada, published their standard for fire resistance S101 in 1982. Standard was very similar to the US-based standards E119 and UL263. So now let's look at the code requirements. And the code requirements, yeah, if you look at all the nitty-gritty details, are quite extensive, but the basic concept is assemblies are tested for fire resistance, or fire resistance ratings are established in accordance with testing in accordance with UL 263 and ASTM E119. Those are the two standards which establish the fire resistance ratings. The organization of the IBC was changed with the 2021 version, and now there's 3 methods of establishing, or not establishing, but confirming fire resistance ratings allowed by the IBC. First is test the assembly in accordance with these 2 standards, demonstrate it has a certain fire resistance rating. Second method is referred to as analytical methods, where the methods are based on the fire exposure and acceptance criteria of the two standards, but there's a series of practical solutions in terms of how you show an assembly has been tested and meets a certain rating. So that's the second method. And these first two methods, very clearly by the IBC, are established without the use of an automatic sprinkler system or any other fire suppression system being incorporated to help achieve that rating. The third method of determining fire resistance is through the use of the alternate methods and materials provision of the code. So it says that the fire resistance of building elements, components, assemblies not complying with these first two methods shall be permitted to be established by the alternate protection method in accordance with section 104.2.3. That's the old section 104.11, just renumbered with the 24 version of the code. So any case, this would be where fire suppression could be combined with fire resistance to achieve that fire resistance rating. But any case, so that's what the code reads nowadays. Now, if we go north of the border, we go up to Canada, we have the National Building Code of Canada, which likewise establishes the requirements for determining fire resistance. And it's very much like what we have here in the States. It says the rating of the materials, assemblies, or assembly of materials or the structural members that is required to have a fire resistance rating shall be determined on the basis of test results conducted in conformance with CAN ULC S101. So likewise, that is the basis for establishing fire resistance ratings up in Canada. Okay, so now let's switch gears and talk about fire stopping. And fire stopping, has been around in various forms for a lot of years. In the early days, the codes would simply read that the annular space around the penetrating item should be protected with a material which will prevent the free passage of flames and hot gases. A relatively vague phrase, didn't say what the material was, had to be an approved material, in other words, something acceptable to a code official, but these were not, tested systems are not proven to work through actual fire tests. They were just intuitive methods. And, most of the time the concept worked, sometimes it did not. Won't get involved in reviewing some of the situations where it didn't work, but truly there were some issues with that concept. So the fire stopping as we know it today really originated, unfortunately, as a result of another tragedy, the Browns Ferry nuclear power plant fire in 1975. The fire stopping consisted of a foam plastic covered with a fire retardant coating, and that was judged to be a contributing factor to a near nuclear disaster. And this fire was really pivotal in the development of fire stopping as we know it today. So shortly after that Browns Ferry fire, UL, along with the code writing groups, recognized the need for a more robust fire stopping. And UL began work in developing a test method in 1975. So literally 6-8 months after this fire occurred, UL began doing research to try to develop a test procedure for fire stopping. And first listings were actually published in 1976 based on a draft test method that had not yet been finalized, but that's sort of how things oftentimes develop when new test methods come into play. So ultimately, the research that UL did was intended to develop a unique fire test standard which complemented UL 263 and ASTM E119, but addressed the unique requirements of a fire stop system. So what are the unique requirements? Certainly sample size. You need a 14-foot by 17-foot test sample to evaluate, for example, the fire stopping of a 4-inch EMT conduit? Probably not. You can make use of a smaller size assembly, as shown in the photo on the right. And what about differential pressures? Fire stopping materials are oftentimes elastomeric materials. As they dry, shrink, they can form cracks. Those cracks could allow flames and hot gases through that opening. So what we wanted to do is create a positive pressure within the furnace to attempt to drive those hot gases through any cracks or voids that might develop during the course of the fire testing. Something that really is not a concern when you're doing a fire resistance test on a floor assembly. And what should the length of the penetrating item be? And how do we measure temperatures and on the penetrating items? Do we need to measure temperatures? And what about the thermocouple pads? The E119 had some relatively large thermocouple pads over the thermocouples. Those maybe wouldn't fit on a relatively small sample. So there were a lot of things considered. The other, perhaps more basic concept is, if we have a metallic penetrating item, it's going to get hot. Metal conducts heat, and so a metal penetrating item may not meet the unexposed temperature requirements of ASTM E119 or UL 263. So the concept of the F and T rating, flame and temperature rating, was developed for this standard. So ultimately, the first edition of the ASTM E814 was published in 1992. First edition of UL 1479 was published in January of 83 rather. And then the first edition of the Canadian standard, ULCS 115, was published in July of 1985. Now, I also mentioned the first edition of the UBC standard 43-6 was published in 1991. Now, for those of you perhaps not in the US, or those of you who are relatively new to US codes and standards, UBC was the Uniform Building Code published by ICBO out in the West Coast. And at that point in time, they actually developed test standards, fire test standards, and other standards that were referenced in their code. So the UBC standard 43-6 was in reality identical, or essentially identical, to ASTM E814 and UL 1479. When I start talking about the code requirements for fire stopping, you'll see why I've referenced that standard. Over the years, of course, we also had some evolutionary changes to the fire stopping standard, UL 1479 and ASTM E814. One of the changes which took place was the addition of the L rating, or air leakage rating, into the standard in 1993. And the original test methodology was developed in Germany and was adapted to fire stopping by UL back in the early 90s. And it was similar to what is also done in the door industry. So the L rating methodology was added to the standard in 1993. It's an optional rating. It's not required in all cases. And ultimately, whether it's needed or not depends on how that fire stop system is being used. What type of barrier is it being installed in? If it's being installed in a smoke barrier as defined by the IBC, then the fire stop system needs to have an L rating. And then there was some, specific criteria set up in terms of differential pressures between the two sides of the fire stop system. Test was conducted at both an ambient temperature and at 400 degrees Fahrenheit to represent cold and hot smoke. And ultimately, the methodology that UL chose to use is to publish the actual numbers, the leakage numbers, and then let the building code make the decision on how much leakage is appropriate. And that was a big stumbling block when that method was developed, is how much leakage is acceptable? How much toxic gases can you allow to pass through that barrier? And UL chose to use the word air leakage instead of smoke leakage, with the idea that perhaps that might speed up the code adoption of this methodology if we thought of it as air leakage as opposed to smoke leakage. But that didn't prove to be the case, because ultimately the code requirements relating to L ratings didn't get into the International Building Code until the 2006 edition. So it took 13 years from the publication of the test method to the adoption of code requirements. So another change which took place to UL 1479 was the inclusion of a W rating, or a water rating. That was added to the standard in 2004. And the original intent was simply to determine, will that fire stop system prevent passage of water through the system under a certain standardized condition? And the more we thought about it at UL, the more we said, no, that's really shouldn't be the main focus. Yes, water leakage is important because it does cause, physical damage to the building and that sort of thing. But more important than just the fact that water leaks from one floor to the next is, if these fire stopping materials get wet, will they still provide their fire performance? And that really became the focus of the W rating after we thought it through and came up with this methodology. So once again, the methodology that was developed is to subject the fire stop system to a water exposure, 3-foot water column for 72 hours. And then if there's no leakage of water, then the water is removed, the assembly is dried up, and then it's subjected to its fire exposure test, host stream test, and the F&T ratings are established after that exposure to water. And once again, this is an optional rating. Ultimately, it's not a code requirement, so it's really up to the discretion of the building owner to determine if they really want that added benefit of the fire stop system. So ultimately, the publication of the standard led to a number of rating identifiers. Under UL 1479 or ASTM E814, we have an F rating, which relates to passage of fire and successful host stream performance. We have a T rating, which relates to flame passage, temperature criteria and limitations on the unexposed surface, along with successful host stream testing. The L rating, of course, is the air leakage test. W rating is that water leakage test. And then the M is a movement rating. Criteria is not in the standard, but the methodology has been developed, and the UL is now establishing M ratings on fire stop systems that are movement cycled. I should say the penetrant is movement cycled relative to the barrier prior to the fire test. Fire test is conducted, so it demonstrates that the penetrant has the ability to move within the limitations of the listing without impacting or damaging that fire stop system. So up in Canada, their standard ULCS 115 is a little different than our standard in the United States. And the basic difference, the primary difference, is the fact that the host stream test is an optional test procedure. So when we say in the US an F rating, we imply assembly meets the flame passage and the host stream performance. In Canada, that host stream is separated out from the F&T rating. So an F rating shouldn't say simply, but it strictly relates to passage of flames through the fire stop system. An FT rating relates to passage of flame and temperature limitations on the unexposed side. If we add that designation H, now that assembly meets the host stream. So an FH rating is a system that meets both the flame passage and the host stream performance. An FTH rating is something that meets the flame, the temperature limitation requirements, along with the host stream test. And then likewise, they also have an L rating requirement in Canada, similar to the requirement that's in place in the US. So that's the primary difference. There's one other difference which I'll address when we get to the code requirements. So very briefly, I'm going to show you a couple slides that relate to how these systems are tested. So this is a photo of a concrete floor assembly with various penetrating items passing through it, fire stop in certain ways. What you're looking at is the top of the assembly. There's a number of wires on the top of the assembly. Those wires are in reality thermocouples, which are used to measure the temperatures on the unexposed side. So then that assembly is subjected to a standardized time temperature curve fire exposure from the underside. This is the same curve that's used for basic fire resistance, and Gabby is going to show you the differences between that US-based time temperature curve versus some of the international curves. They're similar, but certainly not identical. And after the fire exposure, the assembly is lifted off the furnace. This is a photo of assembly being removed from the furnace. You can see the plastic penetrating item that's over here in the background has melted away. That intumescent collar has closed up, prevented passage of fire through the floor assembly. We have a cable in the foreground, large metallic pipe, and I believe this is an EMT conduit in the foreground. But anyway, those assemblies are then subjected to this water host stream test. It's a structural integrity test, an impact test that demonstrates the system has the ability to remain in place, has sufficient integrity to remain in place in this very dynamic fire environment that we could have items dropping down from the ceiling, items impacting the penetrant. So we want to make sure it has enough integrity to stay in place. So let's look at the code requirements in the US and then ultimately in Canada. And remember I talked about the UBC test standard 43-6. Well, the first US code requirements that actually spelled out furnace-based testing was in the 1991 Uniform Building Code. It required penetrations in walls and floors to be protected with a system having an F&T rating respectively when tested in accordance with UBC standard 43-6. So that was the first code reference to furnace testing. ultimately, we've jumped forward many years to the current day International Building Code. Section 714 covers penetrations or the protection of penetrations, and it says through membrane penetration shall be protected with an approved through membrane fire stop system tested in accordance with ASTM E814 or UL 1479. So those are the two test standards which are required for evaluating fire stop systems. And for penetrations through wall assemblies, those systems need to have an F rating, not less than the rating of the wall. For floor penetrations, the system needs to have a T rating, not less than the rating of the floor, with some exceptions. And so are some exceptions in the code where that T rating is not required. When that occurs, the base requirement becomes an F rating only. Up in Canada, there's similar requirements in place in the National Building Code of Canada. It talks about for penetrations of vertical fire separations, an F rating is required. That F rating shall be not less than the rating of the wall assembly. For penetrations of horizontal fire separations and for fire walls, an FT rating is required, and it shall not be less than the rating of the floor. And again, there are some exceptions to the requirement for that FT rating, the default being an F rating where an FT is not required based on these exceptions. And it's kind of interesting that the same basic concept applies in Canada as in the US. Penetrations through vertical assemblies require an F rating, penetrations through horizontal, an FT rating. Now, the one thing that's unique in Canada as compared to the US is penetrations through fire walls, which are that most sacred type of a fire resistance rated assembly, is required to have an FT rating also. So that's a different, more stringent requirement than we have here in the US. And then moving on, outlet box penetrations and fire separations are required to have an FT rating, not less than the rating of the fire separation. Again, there's one exception to that requirement. And then for combustible outlet boxes, once again, we need an FT rating, not less than the rating of the floor. I believe that should read wall and not floor. Sorry about that. And then the unique requirement of Canada is that where you have a combustible drain, waste, or vent pipe, you need to protect it with in a building of 4 stories or more, you need to protect it with a fire stop system that has been subjected or has been tested with a much higher positive furnace pressure as compared to other types of penetrations. Typically in Canada, for a typical non-combustible pipe, you would test the system with a 2.5 Pascal positive pressure within the furnace. For these combustible drain, waste, or vent pipes, these buildings more than 3 stories, you're required to test it with a 50 Pascal positive pressure between the exposed and unexposed side, with the higher pressure, of course, on the exposed side. So the idea there is it's trying to take into account the stack effects which would occur in a shaft, a multi-story shaft, where you have a very significant pressure differential between the shaft and the rooms adjacent to that shaft. So anyway, so that completes the discussion of the North American test standards. So now I'm going to turn the floor over to Dr. Peck, and she will talk about the requirements elsewhere in the world and compare and contrast to what we do perhaps in the US and in North America in general.
Rich, are you passing the slides? You need me to do that?
I can change presenter.
I got it.
You got it? Okay. Beat me to it.
Very good. Awesome. So next up, Dr. Gabrielle Peck joins us from New Zealand. So Gabby, the floor is yours. Just need you to show your slides on the correct screen and off you go.
So I haven't used this before, so I just don't seem to have the slides on my screen.
Well, if you'd like, we can just run it from mine and off we'll go.
Yeah, that would probably make it a bit easier. Sorry.
There you go. No, that's all right. No worries. There you are. Can you see it okay?
Okay, I can. I'll just say next, if that's okay.
Perfect.
So I'm talking about fire testing and fire stopping standards across the UK, EU, Australia, New Zealand, and China. So it's a lot to cover. It won't be as in-depth as Rich has gone through, but it should be quite a nice high-level overview to kind of get a picture for the rest of the world. So next, please. So in terms of fire resistance testing, obviously North America uses the UL 263 and the ASTM E119. Now, they're not really used anywhere else across the world as much. So in other countries, we have our own kind of versions of them. So in the UK, it's the BS 476. Now, there are 31 parts to this standard, and it's 20 to 24 that pertain to fire resistance testing. Now, in the wake of Grenfell and the government inquiries, it was decided that we would shift away from using the BS 476. And in place, we're switching to the European standards instead. So it's a bit more conformity in that sense. It's still remaining a British standard, so it's applicable in countries like Hong Kong still, but just not so much in the UK. And there's a whole complicated wormhole to go down in terms of existing buildings, new buildings, and that transitionary period. In the European Union, we use the 1363 series, so that's 1364, 65, and the 13501 Part 2. Australia and New Zealand actually share most of their standards, and for the most part, this is covered in the AS 1530 Part 4, which is currently undergoing experimental changes and proposed changes, courtesy of, that's my job currently as well. And then in China, they use the GBT 9978. So the whole point I want to focus on is how they actually differ from the North American standards. So next, please. So in terms of similarities, they look the same. The setup is pretty much the same. You have some slight variation in furnace size, but it's all a very similar setup, very similar design, same style test reporting, and it's ultimately used for the exact same thing. But there are two key differences from the North American standards to all of the ones that I just mentioned, and that is that we all use the ISO 834 fire curve, not the ASTM, and we also don't require the use of the hose test. So next slide, please. So to hose or not to hose, what's the difference? And next slide, please, Bill, sorry. So it's mandatory in North America, optional, but very rarely that I've been in New Zealand for the past year or so now, and I've never seen that being required or carried out. So it's optional in Australia and New Zealand, completely absent in UK standards, absent in European standards, and also absent in the Chinese standards. The only time you see it really present in the Chinese standards is for like international testing, like if they're planning on exporting to the US, but it's not really a common thing. And as Rich rightly pointed out, it's literally to test the structural integrity when it's subjected to cooling and erosion from water following the fire exposure. So next, please. So the whole point of this, it does actually increase the test stringency in general. So you're going to know whether your structure can withstand the cooling effects of water. Can it stay standing during other operations where it would be exposed to fire water in like a real world scenario? Now it is different from the firefighting hose, that is a significantly higher water pressure, but it is there just to indicate how is it going to perform under these scenarios. Now, you might be like, why is it not there for the rest of the world? Now, our fire resistance testing only really focuses on the actual fire resistance during exposure. So does it maintain its integrity, the insulation and load bearing capacity? We don't look at post-fire durability at all in these standards. It's just not covered. Next, please. So you can say, in that sense, the North American standards are much more stringent and rigorous, and you probably feel a bit safer knowing that your building structure and your penetration systems are all going to function after being subjected to water. But again, it simplifies testing for the rest of the world, but we're kind of overlooking the post-fire vulnerability of our buildings. Next, please. So the other key difference is the time temperature curve with the North American standards and again the rest of the world. So we all of the standards that I've mentioned all use the ISO curve. So you might think, oh, well, they do look quite similar, and they genuinely do, but there are some subtle differences. So if you press next, please. So I've put in the actual furnace temperatures and the ranges, and I've color coordinated it so you can see red is the lower temperature, green is the higher temperature. So you can see clearly when you look at the ASTM, the first two columns of ASTM and ISO, that there are slight differences. And typically speaking, the ISO curve runs a bit hotter, but the nuance lies in the ranges and tolerances that we actually allow. So the ISO curve initially has quite a wider tolerance, but then ends up with more stricter controls versus the ASTM is a bit of a broader range. So you can see the color is a bit all over the place in this sense, but typically speaking, what ends up happening is when you conduct these fire tests, like the European tests, British tests, anyone that uses the ISO test, the furnace tends to run a bit hotter, which makes for a bit more of a harsher test, generally speaking. So next, please, Bill. So when you look at the actual nuances of the test differences, you know, a product tested using the ISO curve, you're looking at potentially an earlier failure, just if you've got a material with slightly lower thermal resistance, just because the furnace does run a bit hotter. So you could say it's slightly tougher for shorter duration ratings, but they do end up matching up towards the end of the test. So long duration tests, they end up quite similar. But you also have with the North American standards, the difficulty in passing the host stream aspect. So they're similar but very different, and that subtle nuance does make all the difference in terms of product testing and looking at the systems. To say one is better than the other is completely different. In an ideal world, we would try to merge them and combine the safety features of both. So the fire stopping standards. Thank you, Bill. And again, if you don't mind. So I'm not going to focus on this slide too much. This is more here for those who kind of come back and want to look at the actual comparisons between, okay, so this is the US standard, what's the equivalent used in the other countries? The one thing I will point out, if you notice, so the European tests have like the different parts. Australia and New Zealand pretty much just uses AS 1530 Part 4 and 4072 Part 1. So it's all kind encompassing rather than individual set requirements. So next slide, please. So in terms of what differences they actually make, in terms of a pretty high level overview, so in terms of smoke leakage testing, it's pretty standardized, as we saw from Rich's slides, quite standardized, and you do ensure that your fire stop systems control smoke spread, which is a logical approach. Internationally, we don't do that. It's optional and a lot less standardized. So the European Union testing, like the Euroclass system, is quite good in that you have a Euroclass rating for the combustibility, so A1, A2, how does it burn essentially, does it burn? And then you have a D code, so D0, D1, D2, so does the material melt and drip? And then you also have an S code, which is the smoke of S0, S1, S2, so how much is produced during the test. Australia and New Zealand just completely do not do that. That is another thing that I've been working on for the past year, is facilitating that to be integrated into these kind of standards. And then interestingly, in China, it doesn't actually look at smoke control, but it more just focuses on how toxic are the emissions from that test. So it's similar, but still that subtle slight difference. So next slide, please. And the main thing that means to the contractors are that, you know, you just have to be aware that if you're going to be working in different countries, like outside of the US, and vice versa. Just the ratings on the products may not be applicable to other countries. So you probably wouldn't be able to use a lot of international products in the US because of that difference in testing and rating. And it's also being aware that, I know members of the FCIA are very passionate about what they do, but being aware that if you install the system in places like Australia and New Zealand, you are not going to be required to offer the same level of smoke protection. Now, it's not a judgment on any contractor's behalf, it's just making sure that you're aware that you might meet the standards, but it might not do the job that you hope it would in terms of meeting the actual codes of these countries. But it does open a lot of doors for organisations like the FCIA to come in and advocate for significant improvements and better standards and better ways of doing things. Next slide, please. Then in terms of the movement cycling, so in terms of if you have an earthquake and your building shakes about, does your fire stop system actually still maintain what it's supposed to do? Is it still effective? So that's mandatory in the North American testing, but optional everywhere else. So next slide, please. So to point out the interesting dynamic of this, so I've been in New Zealand for the past year or so, and I've been woken up by earthquakes about 4 or 5 times this year. It is not considered here, which is very deeply concerning. So you have no idea if what's been installed as your fire stopping systems are still there. In terms of the European Union, it is included. It's optional, but all of the protocols for testing are very different. And then again, in China, it's very similar to New Zealand and Australia in that it has high seismic activity, but it's not mandatory to test for this. Next slide, please. And then in terms of the installation criteria, so this is a lot of information that I'm obviously not going to read through every single aspect of this, but I have color coordinated this so you can see that in terms of the criteria, it is pretty similar. They all test on the unexposed side, the temperatures measured from similar positions. The main differences is that in the US testing, they use the average temperature, so excursions above 181 degrees Celsius. They're allowed as long as it stays below a certain threshold. With other countries' testing methods, so the EU, if you actually have a temperature increase above the limit, you end up with an immediate failure. And that's the case for the European Union, the UK in the BS 476, but obviously it's transitioning to the European Union testing, so similar. And then in China, again, but their limits are optional and basically dependent on the application. So next slide, please. So what that means in terms of this is the criteria for products, it differs. So something that might pass in the US could fail in the EU or in China just because of those stricter requirements. So it's very much just making sure that you're aware of this, like the region-specific products and things like that. So next slide, please. So one thing I did want to brush on is the cases where the DIM model of the FCIA haven't reached and the impacts that that has. Because working in New Zealand for the past year or so, it's been quite eye-opening to say the least. And I think we'd all agree that, you know, doing the standard comparison, they all kind of look pretty similar. You'd say, okay, well, the Australian, New Zealand standards, you know, they are a bit lax, but they surely do the same thing. But how they're applied makes all the difference. So next slide, please. So like I said, they've got similar, these standards are recognized in other countries, but is the application the same? So next slide, please. I have so many slides, I'm sorry. So in New Zealand, the building code is performance-based and it allows for alternative solutions. Now, the alternative solutions are used quite a lot. So if you've ever been to somewhere like New Zealand and you walk around, you'll notice all of the buildings are completely different, and they're all unique. Now, the problem is fire stopping is not very well regulated. It's not inspected adequately, which is something that Australia and New Zealand have both been, like fire safety professionals have been going, we need to do this. And it is often ignored. So next slide, please. So after the process of installation, you are required to have your installation systems inspected, and that is conducted by the building consent authorities. But the criteria is not very stringent. It's, does it meet the code, satisfied on reasonable grounds? Now that is completely and utterly subjective. So one inspector might say, yes, that looks good. The other inspector might say, no, that's a terrible job. But there's no uniformity across. And because of that lack of prescriptive requirement and all of that variability, it's not something that's adequately enforced here. So next slide, please. So it is something that is often inconsistent and overlooked. And there's also no mandatory training requirements or education requirements or even experience requirements to actually install these systems. And if you have someone that does a bad job of it and you have an inspector that just says, oh, she'll be right, which I cannot tell you how many times I've heard that, then you end up having best practices completely ignored. Next slide, please, Bill. The other aspect that is a massive, massive problem in New Zealand is the use of engineering judgments. So I know they are present and can be used in places like North America, but the way how they're used in New Zealand is kind of as a cost-cutting loophole, which it is a massive problem and is something that the New Zealand Building Code adjustment process that we're going through is trying to address. So with an engineering judgment, you can claim that you don't need fire stopping because you have alternative measures like sprinklers. And your building consent authorities tend to accept these without rigorously going through that. The other interesting part is that with the New Zealand Building Code and the Building Act, you do not have to be a qualified engineer to do this. Quite literally, anyone can do this. Mary in the post office could put in an engineering judgment if she really wanted to. And if someone in the Building Consent Authority says yes and gives a stamp, then Mary's judgment is final. And that is a massive, massive problem because a lot of the time fire stopping is completely overlooked and an EJ is used and put through and they only have to provide a rationale at some points or just some calculations. You know, they might request some test data, but again, it's a bit unregulated in the sense of it's dependent on the person that looks at your paperwork. So next slide, please. So that's all kind of put through to save on building costs, but fundamentally it's at the risk of people's safety. There have been a number of cases in New Zealand where they've had disastrous earthquakes where you've had partial collapse of buildings and they finally got to see inside the buildings and noticed, oh, they actually haven't put in any fire stopping at all. And that is the state of places where it's not heavily regulated, that we're trying to push them to do the right thing. And this is the harsh reality of places where the DIM model hasn't reached. So your standards and codes all might look comparable on paper, but the actual application is very different. So that's an absolutely grim note to end on, sorry.
Well done, Dr. Gabby, really appreciate it. Any closing comments? We got questions we're going to get to right away, unless there's some other comments that came from others before I hop into the questions.
I'll just jump in pretty quickly to say that this is exactly the kind of intent that us as a larger collective mind, if I can say, or a growing collective mind of the passive fire protection industry is attempting to do, is to increase the awareness bring out, what is the common intent, as well as, pool in the resources of knowledge and comprehension. And I'm very excited to say that, while, Dr. Gabby talked about the lack of the IIM approach, it is interesting to note that in the recent years, more and more governments are starting to look at passive fire protection as a very, very important means to assure fire safety. And not only that, there have been more decisions, court decisions, which have brought about the need to quantify liability and responsibility. A big decision in Australia a couple of years ago for the La Crosse fire incident, brought to light a very large commercial impact on the stakeholders involved in the journey of bringing about fire safety or bringing about the asset itself. And I'm very excited to say that, we are more accessible now as an association. Some of the members here may be aware that SCIA, as an industry association, earlier this year signed an MOU with the Fire Protection Association of Australia, and I would be visiting the Fire Australia exhibition and conference, and speaking with stakeholders as well as industry members and some of my friends who now are risk assessors in the insurance industry, to share the easily accessible and available tools that can be very easily brought into play. I also want to touch upon a very subtle point, through the course of what Rich had talked about earlier, and when you talked about a lot of standards having the capability to quantify data. So for example, we talked about the L rating, the W rating, and so many other data that can be brought out for compliance, which may not necessarily be part of the building code, but that does not mean that it is not used. The fact that there exists an industry consensus to bring about a standard, it means that it is either already being used or can be picked up. It may not be accepted as a consensus among a government entity or a body of larger knowledge, but there are several groups of industry who use these standards. And a classic example is the DIM framework itself is widely adopted and accepted in the healthcare industry, where international healthcare accreditation bodies, use the intent and sometimes the content of our DIM framework directly. And many international hospitality groups are also using the same. So I just want to kind of bring to light, A, that there exist standards which may not be fully codified, and B, also talk about the fact that what Dr. Gabby, you brought about the difference between the standards and how some of them are more stringent in the shorter span of 30 to 60 minutes. The intent of DIM is to educate the users and the stakeholders to make sure in that part of the world they understand how compliance is delivered and how our tools can be used to expand upon that harmoniously. Back to you, Bill.
Thanks, Abhi. Really appreciate it. Questions that came in. One is, I think, pretty important on as far as the if you will think about the different countries have different cultures, and the building codes and standards can really form a culture, if you will. What's required where? A comment came in from a friend that says in the U.S. we promulgate prescriptive codes with performance-based options that must substantiate equivalency. So what I've done is put up the International Building Code 2024 version. Rich and I worked on this 10423 section the last 4 code cycles, actually, probably, by the time all said and done. A person from the sprinkler industry advocated for this 10423 to have some pretty prescriptive things about alternative materials and methods. Note that first, an alternative material method design and construction has got to be approved in accordance with 102.3 through 102.37. 102.34 is probably what screams the loudest at us. And we were involved, Rich and I, on writing this section. And what it says is the alternative material design method of construction shall, for the purpose intended, be not less equivalent of that prescribed in this code. So that means when we talk about fire safety, to be equal in quality, strength, effectiveness, and durability, we should be referring back up to Chapter 7 of the Building Code, where it talks about what the requirements are for fire testing. Rich earlier put up the alternative designs where it's supposed to be in accordance with the E119 UL 263. So pretty amazing that although it's talking performance in a mix, it's sending you back to the prescriptive to evaluate whether this performance is equal to the prescriptive. Kind of an interesting twist on it, if you will. Another question came in, are the hose stream standards or the hose stream tests, in other words, being considered in other countries where they're currently not required? And I guess I'll start and let others hop in. We've got friends that attend the ISO meetings, the ISO meetings on the fire stop standards, and you know, North America is really the only place that mandates, other than some projects in the United Arab Emirates and some in Qatar. But I'm not sure about India. Maybe Avi can give us a little more insight into that. But we only have one vote, we meaning the North American folks. If you think about it, Mexico, Canada, US, that'd be 3 votes. And then all of the countries equally get 1 vote as well. So if those that don't want the hose stream don't want it, then it's pretty easy to outvote the countries that have the hose stream. Avi, you're leaning forward. Go ahead.
Well, the building codes from North America have made their way to Saudi Arabia, for example, specifically, and some of the other Gulf countries like Oman, who are currently interacting with the ICC to publish the Oman version of the building codes. And a lot of times, many of the building codes from the US, either directly in content or sometimes often in intent, are adopted at least in the Gulf countries, but also in other countries where they may not have been directly adopted as the local building codes. But this has got to do more with the consensus that I've mentioned a couple of minutes back, that there are times that industries rely on certain broader consensus documents, and this is building codes, this is technical specifications, and sometimes even conformity of material or system behavior. And hence, the conformity demonstrated through the North American test methods, whether they are the UL or the Canadian or the ASTM methods, is sometimes specified in order to bring about continuity. But yes, what you mentioned, Bill, is right, that there are several other parts of the world who do not have the hose stream test at all in the testing approach or the methodology they use, or the way the methodology has evolved in other parts of the world.
Understood. Next question that came up is, let's see, back to the EJs, if you will. Is there a mutual recognition agreement we can use to accept EN standards in US and Canada and the other way around. So for that one, that's kind of interesting. I can tell you that 10423 section is really what you'd have to do for equivalency. So let's say the material was tested to ISO 834. If it had the hose stream test, then the building official is supposed to compare the two test standards, compare whether it's got the hose stream or not, see if it's got an L rating, if it's required for a smoke barrier in the terminology of the International Building Code, and see if it's acceptable. You know, Gabby mentioned there's some differences in the time temperature curve. That'd be another discussion. Does it make a difference? It might in some of the materials, as you heard Dr. Gabby mention. So that's how the evaluation would take place, is really coming into the US, it would have to be each jurisdiction where that building is built would evaluate for equivalency based on what you see in 10423 through 104.237. And that decision would be made by the code official. Hard part is many code officials are very sophisticated in the larger jurisdictions. Some of the smaller ones, you'll find some very sophisticated people that decided, I'm going to move out to where I am currently. It's 1,500 people in our town, 10,000 in our county. In Chicago, where we live, there was 1 million in our county and 60,000 people in our town. A town of that size can afford a lot more than a town of 1,500 or a county of 10,000, but some people choose to live in those areas, and they may be very sophisticated, so they may be able to do that. The qualifications of those judging it, you know, I can tell you that some building departments would look at this and say, I'm not qualified. If you want to get this equivalency done, then let's find some other data and see what happens. Rich, comments? Abby? Gabby?
I'll make a couple comments on that too. Certainly I've witnessed thousands of fire tests over the years on fire stop systems, and I think it's pretty clear that passing the hose stream test is probably the more difficult of the components of the U.S.-based fire stop testing as compared to the fire exposure. So I think it would be difficult to try to justify a material that was tested elsewhere without hose stream is acceptable to the U.S.-based or based on the U.S.-based requirements, which include hose stream tests. I guess probably in all honesty, if I was a code official myself, I probably wouldn't accept something that had not demonstrated satisfactory hose stream tests. So now, can that be overcome? It probably can be if the testing agencies in other parts of the world can develop the capabilities of running that hose stream test, even if it's not required in their country. In recognition, there's a lot of manufacturers that could be running tests at their laboratory and planning on importing those products into the US. So we could probably overcome that side of things relatively easily. Now, the other issue, as Bill said, is the knowledge of the code officials. Now, I have full respect, a lot of respect for code officials. I mean, I am an expert on one little section of the IBC. They have to be experts on the entire book. And well, by the way, frequently they're combination inspectors who have to be experts on mechanical code, plumbing code, electrical code, et cetera, et cetera. So they can't possibly be expected to have the same level of knowledge of people like us. So when I was with UL, a lot of my time was spent educating code officials, helping code officials, both in a formal setting in a training class, but also on a one-on-one basis on the phone, where a code official will call and say, hey, I've got a request to consider a fire stop test that was conducted in, you name the country, it doesn't have hose stream. Should I be accepting that? And my tactic then was to discuss what are the requirements of the US-based standards versus the standards that that product might have been evaluated to, give them the information to make the decision. I really can't make that decision for them. They are the authority having jurisdiction. But I like to put those folks into a position that they have the knowledge to make that decision. So I guess I'll say that I perhaps see that as also partially a role of the associations too, to educate people, make them aware of the differences so they can make an informed decision.
Well said. Couple things. I've had some questions come up about inspection. And I can tell you that the inspection in the International Building Code is, as you see on your screens, required for certain types of buildings. High rise would be 75 feet and higher above lowest fire department access, and then risk category 3 and 4 are critical buildings, hospitals, schools, water treatment plants, police stations, etc. Now the next question is, how do you qualify the people that do that kind of work? Look at what they've done in the smoke control section. They've got something about expertise. In the 2027 version of the building code, it'll say that the fire stop inspection agency person that's doing the work has to pass an industry exam. You know, the FM and UL Fire Stop exam, the International Fire Stop Council has an exam, Washington Association of Building Officials, International Code Council, etc. Then our building code even talks about, and you know, this is what I had mentioned, special inspection. It's mandatory inspection of certain items, mainly structural items, where the building code official says doesn't absolve responsibility but delegates the inspection to a third party that has expertise in that particular discipline. These sections are written to be generic enough to apply to all the disciplines, including fire stopping and fireproofing. The approved agency, in other words, the organization that does the inspection, has to be independent of the contractor, independent of the building owner, competent, have equipment and people. And then if we scroll down, the inspector has to be smart, obviously, and have relevant experience, competency, training in the same type of special inspection or testing activities. So let's say that the inspection that's going on is a structural steel connection and bolts and all that kind of stuff. Can they do fire stop inspection? Sure, if they've got relevant experience and training and all that kind of stuff. So in this scheme, if you will, strategy, very prescriptively written, and it's been around a long time because it was in the Boca National Building Code. I think it might have been in the Uniform Building Code too. So it's been around for decades, probably since the 1950s, maybe 1960s. And it's pretty well organized about how the inspection is to be done. A commenter says there are some inspection regimes for passive fire protection under the building warrant of fitness in New Zealand, but I'm not sure how much they have as far as the detail. So Gabby, if you want to jump in a little bit, feel free.
They do have it written in their building code, but the problem is always the enforcement. That's the issue in Australia and New Zealand. It's always the enforcement. Now, in terms of comparison to what you were just saying, Bill, like you can see approved personnel essentially must have competence or relevant experience and training. The European Union, for example, obviously it's made up of a whole load of different countries and they all have their own jurisdictions, similar to the US, I suppose, but nowhere is it mandated like this. You don't have to have, you don't have to be an approved company. There are accreditations that are available and optional. So in the Nordic countries, you've got the Swedish FPA like accreditations and things, but it's not mandatory. There is a bit more of a global shift, especially in New Zealand, Australia, the UK and EU after Grenfell and all of the like stuff that came to light with the inquiry. It's saying we do need to kind of push for more like what the US are doing. But in New Zealand, the issue is enforcement of what's written. They have a quite a significant problem with enforcement and, you know, cowboy building practices essentially.
Fair enough. This is pretty well documented as to the procedures. When it says approved, approved means approved by the code official when under the International Building Code scheme, and also over in the NFPA 101, NFPA 1 standards, you'll have the same type of language. One quick question came up, not to switch from inspection, but a person asked, what's the difference between UL 1479 and EA 14? Rich, you got any thoughts on that?
I do. From the perspective of the fire exposure and hose stream test, the two standards are, for all practical purposes, are the same. They describe the same test equipment, same test instrumentation, same conditions of acceptance, and so on and so forth. The codes also recognize them to be comparable. Where you see one, you'll see reference to the other in the codes. Now, where they differ is the fact that the UL standard has gone, I'll say, 3 steps further than the ASTM standard. The UL standard has incorporated requirements for air leakage. It's also incorporated the requirements for the water leakage testing, and it also has some environmental exposure condition requirements in the standard for intumescent materials. So those 3 additional features have been incorporated into the UL standard that are not in the ASTM standard. So that's where they really differ. And you could also, I'll mention that M rating, movement rating, where the penetrant is moved relative to the barrier, that's not yet part of either of those 2 standards, but it is a testing methodology that UL and presumably the other testing laboratories are offering as an option to their customers. But so sooner or later, that will be incorporated into the standard, UL standard at least, I'm sure.
Yeah, that likely optional, similar to the W rating and the air leakage rating,
Yes.
or L rating, absolutely. One thing that you hit on earlier was on combustibility and determining that in looking through the International Building Code Development Monograph, which was published a few weeks ago that Rich and I'll go listen to next week. There's probably 4 code proposals, maybe 6, maybe 10, on how to determine combustibility. So although you had put in there in 1908 or 12 or 14 or 15 that the discussion started, guess what? It's still going on. How do you define it? What is it? Which standard are we going to use? Et cetera, et cetera. And it's interesting to watch, because when you go to the code development processes and standards development processes, industries are vying for attention. How do they get their methods and strategies preferred over others? And some use the building code to do that. From the FCIA perspective, you saw ABI spend lots of time on the DIIM. We're focused on heavily on the IIM, and some of the D as well, to make sure the right stuff is used. But really, the manufacturers, the laboratories, they're very well calibrated. They've got controlled environments. As soon as you show up on a construction site, as Gabby mentioned, you wind up with sometimes cowboys that are flinging stuff left and right that really don't care about the intricacies that were taken to make these products work in a laboratory. So that's why the FCIA, the rest of it, the IIM, we've been focused heavily on those 2 things. We're not going to go into it now, but know that that's been our focus as a organization in the building codes. Put these special inspections in the building code for fire stopping, refine it so the right companies and the right people are inspecting. We tried to put in that contractors get qualified too, but we were unsuccessful. Really close, but unsuccessful in the 2009 code cycle for the 12 International Building Code. We lost by 1 vote, believe it or not, at the committee hearings. So we as an industry have been really focused on how do we get the stuff that gets made, sold, installed, inspected, and then hopefully the building owner manager has the culture that they're supposed to maintain it for the life cycle of the building, so that it's reliable and works. That's really been our focus heavily at the codes and standards development processes. So I'm seeing the questions are drying up. I'm not seeing a lot other than the type of thermocouples might be different in European and other things, but I don't know if we want to get into that detail right now. I guess what I'd rather do is ask if there's closing comments from Gabby, Rich, and Abhi in that order. Go ahead, Gabby. Anything from you?
There is a table that people can go back to just in terms of the thermocouple placement details. But yeah, the bright green one that you just went through. Other way. Good. Next. Yeah, that one. That's just detailing the difference in the thermocouple placement, and then the difference in thermocouples. I mean, the US uses Type C. We predominantly use Type K. Main difference is slightly different tolerance. So that's just to address that question briefly.
Well done. Well done. Abhi, some thoughts from you? Uh-oh.
I believe you're on mute, Abhi.
Yeah. Let's let Rich go, and then Abhi can figure it out. Go for it, Rich.
Okay. Now, I guess my closing thoughts is just that it's been great to interact with Gabby and with Abhi and Bill and on this topic. As of a lot of good information has been presented today in terms of the differences and similarities between the standards around the world, and I think hope that will help folks understand where the various standards should be used, and perhaps some methods in terms of how to get additional standards accepted worldwide, and also perhaps that this is a classic example of where the world is becoming a smaller place, as the saying goes, and why should we be publishing different standards in each of the various regions around the world? Fire burns the same in the US as it does in Canada, as it does in New Zealand, as it does in Dubai. So shouldn't we be using the same basic test standards? And I think we just need to get beyond our egos and understand that other parts of the world have good ideas like our regions do, and that we should come together for the benefit of everybody to develop harmonized standards. And I know that process has been going on for many, many decades on fire and electrical, probably every industry. And my personal opinion is we haven't gotten as far as we should have based on the number of years we've been doing this, and we need to continue that effort and see if we can come to some agreements and harmonization of these standards. Wouldn't it be nice if a manufacturer in pick a country, Germany, could run a fire test locally in Germany that would be accepted worldwide? Likewise, manufacturer in China could do the same.
Yeah, but, absolutely. Abhi, I think you should be good now.
Sure, thanks for unmuting. I would like to touch upon, in closing, a couple of things related to so many different standards. And, you did mention about this, that I wish there is some synchronism that happens. I am very bullish about the fact that now the world is much more close. The last decade, post-pandemic, got the world much closer, understanding each other's perspectives and realizing more and more. For example, you mentioned that the fire is exactly the same. There are so many examples where standards have coalesced in the past. The recent most, which I am familiar with, that for solar panels, for example, UL had a standard 1703, and there were IEC standards 61730. But now, all the stakeholders who were in the standard development committee of UL 1703 agreed that we should have one harmonized standard. So 1703 is no longer there. And there are countless examples, whether we are talking of harmonizing plug types, charger types, to so much where people are realizing that there is some benefit in harmonization. In the same breath, I would like to mention that when there was a conversation regarding testing as per the North American standards and testing as per the European standards, there have been several testing laboratories coming from the testing background, where the laboratories have now attempted to conduct the test as per both or several standards simultaneously, having more than one thermocouple type and maintaining pressures which are worst case scenario of both, leading to offering compliance to solutions to several standards in the same go as well. It is not easy. It is in fact tougher, but there are several ways where people are approaching this challenge. So in closing, I just want to say one thing, that we are excited to be the platform which is bringing the industry worldwide together for dialogue. And we are very happy to be able to address and talk about such a complicated issue, saying, well, there is the British standard, there is the EN, there is ISO, ASTM, Canadian. We've covered so much in such a short span of time. So I'm very proud that as a large industry body, we have been able to enable such a valuable conversation. So a big thanks to all the members of FCIA who are enabling us to bring this information out. And we roll the red carpet for more to join in.
Well said, Abhi. Really appreciate it. Again, if you remember, big thanks for paying your dues, because without you, Abhi and I and Rich, the rest of us can't do what we do. So a big thank you. If you're not a member, like to reach in, grab your credit card, have you join right now. Just visit the website, hit the join now, and join up the association, because it's not just a club, if you will. It's an industry advocacy organization for better fire and life safety worldwide. We do a lot in places nobody knows to try to build better fire and life safety. Yeah, we've got conferences and website and webinars and all that kind of good stuff, and they're all of great quality. But it's the other pieces, building the right stuff, the DIIM, that makes the difference at the FCIA, and also the National Fireproofing Contractors Association, who, you know, we work with them as well, and the fireproofing industry is a big part of what we do. So thank you everyone for being part of the webinar. Thanks, Rich. Thanks, Gabby, for being up at the middle of the night. Thanks, Abhi, for being up in the evening. Rich and I are starting our day, so it's no big deal for us. But a big thank you to you guys for hanging on. And Gabby, we wish you a few hours of sleep before your workday gets going again. And Abhi, and say hi to your family for us. Thanks, everyone. And we'll see you next time on our next program.
Okay. Yeah. Thank you, everyone.
Bye-bye.
Bye.
Leave.